slightly better. Right now, this is a non-linear, meaning it's still, you see, it's still a linear model. Okay, but we can make it in terms. We can change this. One of the ideas will be to change this to this pattern. The same pattern that you see in real experiment. So it will be a weighted distribution that we can use, or a similar distribution, maybe a normalized distribution. But at this time, that's the only one we have right now. We haven't validated it now. That'll be the next step. This is more of advanced science that was done recently. Okay, if you consider phase angle relation with vibration of the material, so does vibration really affect more of the structures part here, going more deeper into the material science? I don't know if we have more time here, but assuming that noise is very similar to a harmonic motion, that you're walking on a surface. Okay, so there is a decay, an exponential decay of noise with respect to time. Okay, so that's what you see here. So there could be three components, and this is coming from acoustics, physics. So there are three different components. One of them is stiffness, which is inherent of the material, or which is coming from the E star that I mentioned. So that's one parameter, but there could be strength as well. Stiffness, already inherent characteristic of the material. Then there is mass, which you measure. Okay, but then there is something called C, which is the damping coefficient. So each material has its own damping characteristics. Okay, so it's more of the acoustics that we are dealing with. So advanced science here. So when I actually researched, there was a relationship with phase angle, okay, and the critical damping coefficient. That's there already in the literature. But we haven't used this in terms of how can we characterize noise in pavements. What was done here is that we characterized the same material, okay, because we had phase angle values for all these mixtures. We could characterize into three different zones. One is the stiffness control, damping control, and mass control. The thing here is that mass control is very difficult to really control it, the mass component. Okay, because you'll change it, it can change due to volumetric changes. There could be changes, okay, of the material. And stiffness can be really controlled. If you load the material with one vehicle versus 10 vehicles, so you can actually vary that. So it's really very easy to control. In real field scenario, if you want to control the material's noise, you will have to control this damping part. So what was done was to calculate damping ratios of the material and relate it to phase angle. And what was found here was really interesting. This is actually just 2 months old study, so I included that in this presentation. You see that the black color points here are the conventional materials. Okay, the phase angle values are by itself lower, okay, as you had seen before. So the damping ratios were also lower because they both are directly related, directly proportional to each other. But for asphalt rubber mixtures, it was really higher damping that you saw. The damping ratios are almost closer to about 0.8, and which is what you want to do. You want to have for a material to be really less noisy. When you compare the dynamic magnification factor, this is one of the other parameters that is there in physics. This dynamic magnification factor is a factor that defines if the material really absorbs or reflects noise. Okay, reflects the damping part. And we found that asphalt rubber materials have not only higher damping ratios, but lower dynamic magnification factor. What does that mean? So it actually does not magnify, but it actually attenuates. It reduces noise. So what was done next stage was to actually calculate this. So it was really replicated from the theory. So into 3 different zones, we already have the peak phase angle values. from the experiments, which we already said, yes, that is one of the distinguishing parameters that can characterize noise of different materials. So using that, we could calculate the dynamic magnification factor at peaks, peak resonance. Resonance meaning high damping. Okay, so we found that there was about half a decibel. So we translated the value of dynamic magnification factor that was calculated into decibel scale, normalized to decibel scale, and we saw that actually 10 decibel unit change. So this table is giving you value of noise intensities of two different materials, conventional versus asphalt rubber. And we also have the dynamic magnification factor at peak or resonance, translated to decibels. Okay, so actually we have about 4.5 decibels on average difference here, and about half a decibel here. There could be some shift. Okay, this is still under development, so I'm just showing you some slides here. But we could easily characterize that in damping zone there was a difference of dynamic magnification factor. So how did we relate our phase angle values to field noise? So higher the values of phase angle or the peak values, lower was the noise coming from the field. And we also had the frequencies or the speeds at which this low noise could be achieved for different materials. And you see that here at 43 kilometers per hour, we could achieve the lowest noise for asphalt rubber mixtures. It is about 45, which is about 25 miles per hour, or 30 I would say. So we are able to see those changes here for different materials. That's the same table that you saw in the beginning. So using this, if we know the phase angle values, and if we know the noise characteristics, we can actually achieve this. So this is more of the science or the lab part to distinguish different materials. So same concept can be used for different materials. It could be for polymer modified, or it could be with different proportions of rubber in the material, 10 versus 20 versus 30. Okay, so this is the first part, and I think I covered the whole thing in 1 hour. Okay, I think this will go faster. So the Federal Highway Administration noise model that I showed you in the beginning had one part which could be changed, which was the flow resistivity. As the name by itself suggests, flow resistivity meaning flow is resisted by the material. It's being absorbed. The noise is being absorbed. So the lower the value, the better it is. Okay. How could we actually characterize in the lab? There's no test at all in the world that can characterize that value. If we can contribute these flow resistivity values for different materials, that can be directly input in the Federal Highway Administration noise model. So that will be one of the major contributions from the materials aspect. We used an already existent experiment in ASTM, ultrasonic pulse velocity, that's being used to measure cracks in concrete. Okay. And you can actually get the values of ultrasonic pulse velocity. So here you're impinging a wave in an ultrasonic range, higher than 20,000 hertz. Okay. So we use a transducer which is 25 or 30 or 40 kilohertz or megahertz, and then you can impinge a wave through one transducer and capture that at the end of the other sample, and then translate that into velocity. So basically what you're doing here, you have a sample, you impinge a wave from one transducer and it traverses through the sample, so you're capturing the time it takes from one end to the other. Then you know the sample length, so you can calculate the velocity of that wave, acoustic wave. Okay, it's already there in the ASTM standard. Okay, so how did we do? What did we do with these velocities of the different mixtures? So we could calculate something called the impedance, which is still a material property. You know the velocity coming from the experiment. You know the density of the material. Okay, So from mixed design, if you take the product of these two, you actually get the impedance value. And what is this impedance? It's nothing but the effective flow resistivity that's there in the FHWAT&M traffic noise model, which has the same units, CGS rise. So if you take the product and do some manipulation, you actually get to this unit CGS rise. So what did we do? We had 80 samples coming from University of California, Davis as well, and also from Sweden, and our own ADOT mixtures. Okay, for different asphalt rubber, open graded, without rubber. Also we had no rubber, with rubber, so we had different mixtures. We also prepared some of them in the lab. And these are the field cores. These actually were taken out from California sites. Okay, this came from UC Davis, UC PRC. And we had some field cores from Arizona, California, and Sweden, as I told you before. So these are the pictures that you see. We also had some European mixes with and without rubber. This is the field site, very close, actually going towards Tucson on I-10. We had 5 different mixtures there, and I'll show you one figure which is really interesting. Here it is. The noise was measured at 3 different, in 2002, 2007, 2008, and actually in 2011 we measured it last year, but I don't have that here yet. We saw that asphalt rubber friction cores was least noisy in all the 3 years. And it still functions so very well that there is no crack at all on those pavement sections. I had visited this last year. There is no crack at all, even after 12 years. But the other sections really developed cracks. And to answer your question in the beginning that you asked, do these distresses actually change the course of noise characteristics? It does change. So we saw that when we actually went back to the data, this was taken immediately after construction. Okay. The permeable European mix had no cracks. Okay, in 2007. Okay, but then the cracks started to heal in 2008. So the values started to reduce. And it was the other way around. So the cracks were not there here, and there were cracks in 2008, the values increased. So there is some association with the distress as well. There were no cracks at all whatsoever here. So what happened? So why did the values increase? Mainly because it started to age. Okay, the binder effect started to diminish. So after 11 years of service, it has not cracked, but the noise characteristics have actually decreased. I would say about 99 to it's about 3 decibels change, about half a decibel every year, which still goes back to the same literature that we have seen. So we ran the ultrasonic pulse velocity on the same mixtures that we obtained from Arizona test sections. As I told you, the lower the value, the better it is. So the lowest value for the flow resistivity was observed for asphalt rubber mixtures, which had the least noise and high air voids. Okay, and the other way around, if the value of EFR was higher, the noise was higher too. Okay, and so what could be done using this experiment? Sorry, just 2 more slides and we are done. So we can actually do a laboratory experimental program using this experiment. It's already an ASTM standard, so we are not inventing it. You can, and we also developed a model which I didn't show it here. Okay, we had really excellent correlation there as well. You can capture the velocity values or the time and translate it to velocity and calculate flow resistivity of the different mixtures, and that can directly go as an input in the TNM. So basically what you're doing in the module that we have, instead of really having it as an average here, if you characterize the flow resistivity values of the different mixtures, you can input that here. So you can basically customize